Hello, and welcome to another episode of Undercooled. Today, Tim and I are really lucky to be able to talk to Professor Wenhao Sun, who is going to tell us all about how he's using generative AI in his classroom. This has been a perplexing thing for many of us because students end up using it like it's Chegg. In fact, Gen AI has put Chegg out of business. They were $1 billion company and now they're worth nothing
Right.
because students get it for free.
Yeah.
And so Wenhao's got some great stuff. So, Tim,
Yeah, I think this is a great topic for us to be discussing because over the last year, so many people have said, what can I do? What can I do? What can I do?
Yeah.
And you've actually got something to do
Yeah.
in class with students. So we're really excited to get into it. Before that, can you just tell us a little bit about yourself,
Yeah,
who you
sure.
are, what you do, how you got here?
Great. So I'm an assistant professor here at University of Michigan. I'm the Dow Early Career Professor of Material Science and Engineering. I started here in 2020, so that was right before COVID started, actually. My research group is doing computational material science. And what we do is we try to use advances in thermodynamics and kinetics, where we try to make advances in thermodynamics and kinetics along with computational methods to really understand phase transformations, especially non-equilibrium phase transformations, especially during material synthesis, so how materials form. So my point with all this is that we've been doing computational work for a long time. We've been doing modeling of thermodynamics and kinetics. And one thing that I've gotten very excited about in the last couple of years is the opportunity to use generative methods, generative AI, GPT, LLM, so on and so forth, to help us more quickly be able to produce computational results for calculating things that normally undergraduate students or graduate students don't have maybe the coding background to do. So I have a whole talk today about some of these philosophies and perspectives that I have on this, and happy to get started whenever you guys are ready to share about these slides, or we can just talk about questions first.
well, I'd like to first hear what's your journey been like with
Okay.
generative AI? Because
Yeah.
it kind of came on the scene all of a sudden.
It did.
And it caught us all by surprise.
Yeah.
So we all have our own personal journeys with AI, with generative AI.
Yeah, of course.
So what was yours?
Well, I remember actually I was seeing this is back when OpenAI had like this API playground that was before Chat GPT was released, and I actually sent out an email to the whole department. I said, "Everyone, there's this thing coming," and I think it was like 2022 actually, or 2023. And I was like, "There's this thing coming, and it's going to be radical, and I don't know what we're gonna do about it, but be aware that this thing is on the horizon." So back then, it could already generate text. It can generate very rudimentary code. There's like ChatGPT 3 or not even ChatGPT 4 yet. And it was very, I mean, it was a big change, right? We could all anticipate that a big change was coming. But I think that the recent developments with GPT-4 and GPT-01, which are these thinking models, really that's when I started to get excited about what we could do with this. And that's when I started to be realizing what we could even use it in research, right? It can help us, I think, access ideas that we are not so familiar with. Normally, you might have to go to, like, say, a math department to talk to a math professor about something that you don't have familiarity with. But now you can ask it as if it's this large resource that has the in totality of human knowledge, and you can access it. And I think that when I started using it in my research, and I'll tell you a little bit about what kind of things we do with our research and that. But when I started using it in my research, that's kind of when I realized that we ought to be teaching this as well, and we ought to be teaching how to use this new tool most effectively. I think a lot of students, like you've said, have been using these AI tools to cheat. In other words, to get answers that look okay, pretty good answers to the questions that we've been asking students, and getting that quickly, not thinking, and then getting maybe a good or a bad grade on a class exam. But my perspective now is kind of that, just like when spell check came around and changed the fact that we don't need to teach, or not that we don't need to teach spelling, but like if you spell a word incorrectly in an essay now, that's like that's not allowable, right? It's insane. There's no way you could have that kind of error anymore. I think now Chat GPT responses have become like the new floor of what we should be expecting from students. Like that should be just the first point of of context for a student with an idea, and they need to build on top of that. And I think as teachers, we need to improve the kind of questions that we're asking students, reach higher levels of complexity in our questions for students to be able to exercise these tools to their fullest potential. So anyway, I have a lot of things to show and talk about that, but that's kind of a very high level synopsis of my perspective.
So now that we're sort of at this point of saying, all right, GPT style answers are the minimum threshold.
Right.
This is our minimum viable product that students can do.
Right.
Well, what do you do from there? How do you craft a question that requires students to think and to process information at a higher level than simply looking up information from this totality of human knowledge?
So maybe I can show you a few slides, because I think that a lot of these things I have like visual kind of supporting images that I can use to communicate these ideas better.
Go for it.
Yeah. So I mean, like, by the way, this is an image that I created literally right before this podcast, where we can, generative AI is so powerful that we can create images now. But like, you can see all the problems with the images if you scrutinize closely. And this is kind of the same issues that you see when you start coding with AI, right? You see that it looks pretty good and it probably passes pretty well for a lot of things, but there's a lot of details that you need to scrutinize. And like, if I gave this image to somebody who doesn't speak English, for example, then they wouldn't recognize these errors. But if can read English. But like, if I give code that comes out of Chat GPT to a student and they don't know how to code, they also cannot diagnose and fix and identify issues too. So there's a lot of these kinds of observations that we're making right now as we're trying to do some of these things about using and implementing AI in the classroom that I think are quite interesting and that we're reflecting on. But like I said, the first thing I want to show you is like an example of a student who tried to cheat with Chat GPT. This is 2 years ago when it kind of just came out, and like, I don't know if students thought that we hadn't seen GPT before, but I had asked a homework question where I said, one of the problems, this is a statistical mechanics course that I was teaching, and it says, notice the properties listed in the bottom right of the figure. What are they? So it's like these PV equals nRT kind of terms. The student mentioned, you mentioned properties listed in the bottom right of the figure, but without the specific properties, I can't provide a description.
Oh my God.
Please provide more details or specific properties for a detailed answer. So not only did the student copy the question directly into Chat GPT and provide the answer, they didn't even read what came out of it.
Mm-hmm.
And they just copy pasted it in there. And here's another example where they said, this is a problem where I was having them calculate a phase diagram. And then it says, this is the homework's response. They said, mock data for multiple triplets replaced with actual data. And they didn't replace it with actual data. And so, And so like, those are the kind of things that, I wrote that, like, I said this to the whole class. I was like, you'll be dropped from the course if you turn in homeworks like this. But this is kind of the moment when I started realizing that, like, okay, ChatGPT can produce a lot of this stuff quickly. So maybe we can start moving to more challenging questions. And this is kind of what I use to frame this way of thinking, which is this idea of Bloom's taxonomy. Bloom's taxonomy is this idea that, you have different levels or tiers of learning and thinking, right? So the lowest level is like remember basic facts and concepts, understand these concepts. The next level is like applying ideas to new situations, analyzing and drawing connections among ideas. And then at the highest level, you can evaluate. You can say if this is a good or a bad way to do something. And at the very end, you can create or produce new original work. So I think in terms of academia, I think of like undergraduate level as like understanding basic concepts, remembering basic concepts. In graduate school, we start to learn how to take these ideas and synthesize them into more complicated ideas. And I think research really is the creation of new ideas, right? And my perspective right now is that ChatGPT and AI in general is really good at these low-level things, right? They're really good at remembering and understanding and even implementing really basic rudimentary things, ideas, and execution of those things. But humans, I think us, we are most effective at these higher levels of Bloom's taxonomy, right? Like creating new products, solving problems, deciding what questions to ask, right?
Mm-hmm.
And deciding what kind of questions are interesting and responding to, an engineering need or responding to a societal need. And those are the kind of things that AI is not really doing. It's not coming up with the intent, right? So if we break down our creative work as scientists into intent and execution. I think intent still comes from humans, and it will always probably come from humans. And like, but AI can help us execute on our intent faster. And what I've been trying to think about and understand is how we can teach students to use this tool to help us execute faster. And that's a very interesting kind of a new, direction of pedagogy that I'm thinking about right now. Yeah. Do you want to talk about that? I can keep going with my slides.
No,
Right?
I think that's fantastic because in using it just at this low level as a tutor,
Right.
so many people are building companies based on
I agree.
using AI as a tutor,
Right.
but it's a terrible tutor
Right.
because the student doesn't learn anything.
Yeah.
And so there's no pedagogical value
Right.
for learning
Yeah.
by having something that just gives students answers
Right.
without making them think.
Absolutely.
And there's ways to make them think. You
Right.
can tell Chat GPT, don't give me the answer. Give me a guide for how I can discover it on my own.
Yeah.
And the student gets this guide and goes, I'm not doing that.
Right.
You just go off on the side and find the answers. So I've been struggling with finding any value. And then I talk to you.
Yeah.
And you have this radically different approach
Right.
to use it as a pedagogical tool.
Right.
And so I want to hear about how you do it.
Well, let me talk about what you just said for a second right there, because I think that there are some things that AI, like I said, I think AI is a tool for execution, like quick execution and like deeper execution, and also as a TA to teach you these, things that maybe you're not familiar with. But it still relies on like these intrinsic desires of students, and if you want to cheat, if you don't want to do the work and you want to get a fast grade, AI can help you get there faster. But if you want to learn and you want to go deep and you want to understand all the details, AI can help you do that too. And those are things that I think it's beyond what a tool is, right? A tool can be, for good or for evil, some people say. But AI is just a tool. And I think that we need to teach students to have growth mentality, right? To figure out that, that if they really want to do well in science and engineering, they have to understand these ideas deeply for themselves. And if you want to understand things deeply, AI can help you get there. If you want to cheat, AI could help you get there, but you're just cheating yourself, right? It's a waste of time. And anyone can get that 0 points answer, that, like what I'm saying, the new floor of what a response should be, right? So you don't need to go to university and pay a lot of money to get the education, to get the Chat GPT response, right? What we should do is to do the things on top of that.
Yeah, I think that's really important to emphasize that I know a lot of teacher angst around this topic has essentially been, how do we get around this?
Right.
And fundamentally, we shouldn't be trying to develop technological solutions to fight this technology. It's a behavioral question.
It
It's
totally
this
is.
matter of how do you motivate your
Right.
students to want to do better than this?
I think that, as just like before AI, what were we spending all of our time doing, right? We're spending all of our time teaching content, teaching details of, Fick's law or diffusion or phase diagrams or whatever. But now that we are in the stage where some of the things that are like challenging to execute have become a little easier to execute, now we have to teach the responsibility of how to use these things and how to grow with these tools there. There's also a lot of teaching that we have to do into scientific skepticism, right? Skepticism is a general central tenet of empiricism and the scientific method. And skepticism is important in using AI and leveraging AI, but it's also important in how do we interpret data and things like that. And these are things that in my perspective, we don't teach in classes very much, right? If we start an engineering degree, we're just learning how to execute the methods of engineering. But trying to understand how do we become better scientists, and what is science, and how do we do better engineering, and what is engineering, and how do science and engineering play together? Those are things that we can spend more time talking about now, especially because I think these generative tools, they kind of alleviate some of the mental burden that we have placed on executing some of these topics. I'm probably going to skip ahead in this slide a little bit, but so this is a slide that I put in this course I'm teaching right now, where we're starting to leverage Chat GPT and some of these tools more. But we really don't know how well this course will go. What we're doing in here is we're saying that AI is changing the landscape of education, and I think that new technologies have always been disruptive. I remember when Wikipedia first came out, and I was in middle school, right? And then Wikipedia first came out, and all the teachers were freaking out because they're like, anyone can edit Wikipedia, and so none of it is trustworthy. But nowadays, Wikipedia, it took us a couple years to figure out how to use Wikipedia most effectively, right? And when we use Wikipedia, it's not like we think that it gives you everything. It just gives you a first introduction to a field, and then you follow the references or you read more, and you know what kind of questions to ask to Google,
Mhm.
right? And so, I think graphing calculator, spell check, these were all tools that changed where we devote our energies as teachers, right? Like, if I was spending all this time working on spelling with students, now I can work on crafting sentences or crafting paragraphs or crafting arguments, right? And you don't have to put as much mental burden on the spelling bits. I think ChatGPT is going to be the same thing. ChatGPT is something that you can devote a little bit less energy to, like, if, for example, if we use it for computational material science, students can spend less time worrying about the syntax of Python, or whether we're going to use Python or MATLAB, or if my code is going to run through. It might have logic bugs, and I'll show you in a moment that you can often generate logic bugs with ChatGPT. But at least you're not worrying as much about, like, the debugging, like the coding problems that, like, the computer stops and
Yeah.
like throws up a tag. So those are things that I think might be interesting. And yeah, I think using ChatGPT to cheat is like a boring use of ChatGPT. Of course, you can use it to solve existing exams and homeworks, but what we as instructors now need to do is we need to make more challenging, more high level homeworks and exams, things that access the higher levels of Bloom's taxonomy, and then make our homeworks at that level, and then have students execute ideas quickly to help reach those more interesting questions that we're asking as real, as researchers in science and engineering. So those are some of my perspectives. Also, like you said, using ChatGPT to learn as a 24/7 on-demand TA. I had a student last semester in thermo, and she was a student coming from Ghana, and her foundations in multivariable calculus, in linear algebra, were not so strong. And we were going through class, and she was struggling with a lot of the derivations that we were doing in graduate thermo. And I sat down with her. I said, if I had to sit here and teach you multivariable calculus, it's going to take a long time. But let's just use ChatGPT and tell it the kind of challenges that you're facing. So she sat down with ChatGPT with me, and she said, can you explain to me Legendre transformations, for example? And then ChatGPT gave a response. I was like, did you understand all of that? And she said, no, I didn't understand all of that. I was like, well, what did you not understand? She's like, I didn't understand this line. I was like, just copy that line and ChatGPT say, I didn't understand this. And so then she did that. And then ChatGPT gave another response. And it said, I was like, did you understand this? And she's like, not all of it, and this thing. And so we just kept recursively going down until she understood it. And then, she kind of understood it. And then and then she worked her way back up the idea of Legendre transformations. I'll tell you her grade performance in the class. We have 3 exams in grad thermo. She got a 12 on the first exam. Then she got a 75 on the second exam after we did this exercise. And the second exam is statistical mechanics. The first exam is classical thermodynamics. And so, that was the kind of delta that we got from her leveraging these tools more effectively. And, I think I approached her to, use this tool as a TA, not as a way to cheat, right? Because the exams are all in class written exams. And so you can't cheat with ChatGPT in the class. So just use it to supplement your gap, to figure out what the gaps in your knowledge are, and to patch those up.
Right. And that's another way to drive students into these higher level cognitive tasks. We're asking them to be metacognitive and to reflect on what are the gaps in their own understanding.
Absolutely.
And to be able to say, this I understood, this I didn't. And then they get to be a 3-year-old. Why? Why?
Yeah, exactly.
And if they keep at it, they will eventually get the whole thing.
Exactly. And the thing about boosting your gaps, like, I'm just gonna say, like, if you're like a B student throughout your career, right? You're gonna get 80% of your first year classes, 80% of your second year classes. Now you have
40%.
Yeah,
or
lots
something.
of gaps there, right? You get to the higher level things, and at some point the gaps become so high that students lose conceptual understanding of what's happening. But, like, if they can at the highest level go back and revisit and boost their understanding of some of the basic topics, it's a very powerful tool, and something that, like, has not really been available in the past. And so there's a big opportunity there for learning, not for cheating, right? And so I think that is on the students to do. That's where you have to teach them to have that growth mentality, and to have that, like, I want to get better, I want to understand this kind of thing. That's kind of on them. on us as instructors, I think we have to come up with more interesting homework and exam problems for students to try and execute with these new tools.
Yeah.
So can you give us an example of a hard problem that you gave your thermo class and how you actually solve it? You showed me this
Yeah.
before, and I'd love you to demonstrate that again.
Yeah, so I'll tell you. So one of the things that we do at the end of grad thermo is phase diagrams, right? And so like phase diagrams come in many shapes, and even with just a few simple phases, you can get a lot of different shapes. And so this is like a classic eutectic phase diagram in thermodynamics. And the axes that we see here are the work of solid solution mixing and the work of liquid mixing. And what happens is, like, if I make the liquid more stable, so if you look at this figure right here, or how about this? If I make the liquid more stable, I'm going to the left, right? And so you can see, like, if I go to the left, the liquidus curve moves down in temperature. So the liquid becomes more stable. The phase region increases. So more so if the liquid mixing becomes more stable. If the liquid becomes unstable, then the solid solution dominates, and you can get things like miscibility gaps. You can get liquid-liquid phase separation. If you change the solid solution work of mixing, you get lens phase diagrams like here. And if you go higher, you can get azeotropes, and you can get all these very interesting phase diagrams. But what all of this is the competition between multiple regular solution models, right? So the regular solution model looks like this, right? It's something that we teach in grad thermo. It's like omega XAXB. This is something that we teach in undergrad thermo, for that matter,
Right.
about how enthalpy of mixing and the entropy of mixing compete with each other at different temperatures. And phase diagrams really are when multiple solution models compete with each other, right? So for a phase diagram like this, a lens phase diagram with an azeotrope, what you have is a solid solution at low temperature that has a low temperature miscibility gap. You go to high temperature, you get a solid solution region. You go even higher, you get an azeotrope with the liquid, where you have liquid-solid coexistence. And you go even higher, you have liquid phase diagrams. This is something I can teach in class. I just explained it very quickly. So like, there's, if you're not familiar with these, you won't get it right away. But this is something that we teach in class. We spend several days, several weeks teaching, and students can draw these curves and think about these curves, hopefully. But computationally executing this is a lot of work. I used to assign this problem as one of the last computational labs in my grad thermo class, and it was so much work and challenging to first get all the phases, then get all the equilibrium states, then plot it on a temperature composition phase diagram. So much work that I just made it extra credit, and I also just chose not to do it with students anymore. But I'll tell you the end of the story right now, which is that this year in my undergraduate kinetics class, so students take thermodynamics before kinetics, and so on the first lecture of my undergraduate kinetics class, I tried to use Chat GPT with the students to construct phase diagrams computationally and to execute this matrix in computation, and students were able to do it within 1 hour. It used to be a 2-week homework assignment in undergrad or for graduate students, and now it's into 1 hour assignment with undergraduates. And I'll demonstrate it right now if you're interested.
Yeah.
But it's one of those things, and I'll show you. And before I show you, I'll tell you some of the takeaways right now, which is that if you use ChatGPT to try to execute this in one shot, it won't do it. It will fail in many levels. It'll have lots of logical errors throughout the problem, but it will execute. It will produce a phase diagram, so it won't have any coding issues, but it will have lots of logical issues. To diagnose those issues, you have to be very good at material science. You have to understand the concepts very deeply to figure out where the logic bugs in the ChatGPT response are. And then you can even tell ChatGPT where the errors are, and it will be like, "Oh yeah, you're right. I'm sorry. I'm going to fix it for you," and it'll do it in a very polite way. But if you don't know the material science, you are not going to be able to debug the output of ChatGPT.
Right.
But if you know the material science very well, ChatGPT will help you execute the MATLAB implementation very, very quickly. And that to me is a very interesting kind of space to be in, because it means that a student's expertise in MATLAB has been reduced, right? So like they don't have to know how to do all the plotting with all the marker sizes and the dots and all these things. That's stuff that I would normally have to spend a lot of time on forums looking at, because I don't remember how to do those things, right? And even if I make a figure, next time I make a figure, I have to relook at those things because I don't memorize how to make
Right.
those figures. So ChatGPT is really good at helping us do those parts very quickly now. But if you don't know the material science in it, then it's still going to be really it's not going to be very helpful for you.
Right. So why don't you show us how you actually do this?
So I'll get started. So this is again the first assignment in a kinetics course, which is trying to build a phase diagram, which is kind of following from the last lecture of their thermodynamics course, which will be right before this. But anyway, so this is the homework assignment that I gave, and in the regular solution model, the non-ideal mixing free energy has this equation. And then I want to use MATLAB to plot the regular solution model. And so there's a trade-off between temperature and the entropy of mixing and the enthalpy of mixing. These are things that we teach in undergraduate thermodynamics.
Right.
So let me just show you what this looks like in Chat GPT and MATLAB. Okay, I can go to Chat GPT and say, can you tell me about the regular solution model in thermodynamics and help me make a MATLAB code to plot the regular solution model. A typing speed test. So it'll start generating. By the way, I'm using right here the free version of ChatGPT. This is not the $200 a month one that I actually pay for as well. But I just want to show what you can do with just the very simple models of ChatGPT. So this is the correct equation for the regular solution model. It tells you a little bit about it, and so you feel pretty confident about what it's doing. And then
Variables.
Yeah, variables and so on and so forth. If you wanted to read it, you could and you should. And here's some MATLAB code to plot it. And so it's just generating it, and it's taking a moment. You could even speed this up later in post-production.
That's okay. I think there's a lot of value to seeing it in real time.
That's true. There is a lot of value. You can talk about the MATLAB code that's coming out, CLC, clear, close, all this, getting rid of this is setting up the environment.
Yep.
You're defining a lot of constants. You're making a composition range. And then here we have, some omega values, which are important for the regular solution model. And now it's plotting some of these things. And let's see, we'll just copy it. And so now I just copy this code. It took about 30 seconds to generate. I just drop it into MATLAB. I can just Control V. And then let's see, give it 10 seconds. Well, so this is a great example. Nothing happened, right? It made a mistake. And so I can go back and I see what the mistake was. Invalid use of operator. So I tell students that, and some students aren't so strong in MATLAB where they don't know to copy and paste and create a new M file. So I'll say like pd.m. So I'm going to create a M file, which is just a script that I can run and edit and diagnose as I need to. So I come over here, I see invalid use of operator. So I can literally copy this into Chat GPT to see what it says. You're right. There's a syntax error in the plot function. So normally I'd have to go back and scrutinize it and look at it. And so now it's just giving me a fixed line. So the plot, it's getting fixed. So I'll edit pd.m, and then I'll go back to this plot line. I'll write it like this. Let's see if it does better this time. So this is an important thing to recognize, which is that ChatGPT doesn't get, it doesn't get the right answer on the first try. So look at this. I think that's pretty cool.
It's amazing.
Yeah, immediately it produces several regular solution curves at different mixing energies. This black one is the positive mixing energy. 0 is the
How
zero.
did it know what values to choose?
It just made them up, and they're reasonable values. 5 kilojoules, negative 10 kilojoules. Those are very reasonable values. And so I'm just gonna go over here. I'm gonna comment out this line so we can always see the response. So this is at 1000 Kelvin, right? If we did it at like a very low temperature, and this is, ChatGPT chose to do 1000 Kelvin. If we did, 200 degrees, we would see some of these characteristic curves. Yeah, so now you have the positive mixing enthalpy, this W shape that is very common in these diagrams. If you see here, this W shape, and then you have here. Now, one thing I want you to notice is that ChatGPT doesn't plot it at 0 and 1 because log at log 0 is negative infinity. And so you can just say to ChatGPT, I notice you're not plotting at x equals 0 and x equals 1. Can you just hard code those points in? So notice that I'm coding in natural language, right?
Yep.
I'm telling it what to do the same way that I might talk to a graduate student about editing their research, results, are updating their research results. And so now it's going to plot this all out. It's going to take a moment because the free version, the fat, and the slightly paid for version. So there's 3 tiers that you can use with the OpenAI Chat GPT model. There's the free, there's the $20 a month, and the $200 a month. For $20 a month, you get a lot of capability that I think is quite worth it. And so I encourage students, you have to buy textbooks. You should pay for the $20 a month thing, because a lot of things that can be done very effectively in that model. I'll show you in a moment.
Which version is in the UMGPT?
They have just gotten O1 Mini, which is the cheap version of the thinking model, and I think that that's pretty powerful as well. So I'll talk about thinking models versus non-thinking models in a moment. But this is not the deep thinking model, just FYI. These is like the fast one-shot responses. And I'll show you later. We'll try the thinking model, and you'll see that the thinking model fails. It doesn't do it all in one shot, and the code becomes so long that it becomes quite difficult to diagnose. So what I've coded in this assignment is kind of like you are executing one small step at a time. So right now we're first generating the regular solution curves.
Yep.
And so let's try again. Let's see if this works. So yeah, so now you see the 0 and the 1 points have been hard coded in. So that's kind of nice. It's kind of nice.
Yeah.
Okay. Now the second problem is to calculate the chemical potentials. This is something that we need in kinetics a lot. And so if you know the solution model and you use intercept rule, you can get the chemical potentials. So I can tell right here, can you help me plot the chemical potentials for the regular solution at a given composition of the solution? Chemical potentials of the elemental reference states for the regular solution at a given composition of the solution, using the intercept rule.
Of course, your language has to be very exact.
Absolutely. So
get this.
You have to be able to know precisely what to
want.
write, right?
Yeah.
If I just say plot the chemical potentials, it might not be right. But notice what I've said. Plot the chemical potentials of the elemental reference states, that's A and B in this case, right? A and B. And then add a given composition of the solution. So that needs to be a parameter that I put in there using the intercept rule.
Right.
And so if I didn't know that, and I can show you a version later, or you can try this yourself, right? You can try a version where you ask a bad prompt and it does a bad job. So it's because I understand the content quite deeply so well that it's able to do this. And by the way, what you'll see here is that the first result is going to be wrong. So here it says the chemical potential is d delta g mix, or partial delta g mix partial xa. That is not the right equation. It is the right equation in a non-affine case. So if you do like temperature is partial delta g partial s. But mu is not, because the chemical potential in the situation where you have xa plus xb equals 1, it's called an affine composition space. And so this general form of the intensive variable as the partial derivative of the free energy in the extensive variable is not correct for chemical potential. But I'll show you what happens, right? So let's plot it and let's see what happens. So I copied it. Oh, it's not done yet. Give me a moment. So this is a great example to show students that ChatGPT does things wrong, right?
Yep.
So I will plot this. All I'm doing is I'm replacing this code, this pd.m code that I keep on working in. And so I just say pd. Okay, so notice here, notice here that this line is not really a tangent line.
No.
It's making a mistake. And also, look at this. This is when the chemical potentials intercept at xa equals 0. And this is the intercept at xa equals 1. So it's having a mistake, right?
But what's strange is if you connect those two black dots, you actually get the tangent point.
Maybe. If I look here with my eye, I think it might not be correct either. But let me talk to ChatGPT, right? And I'll say, so first of all, if I look at the equations, because I tell them what the true intercept rule is, and I can go back and read the prompt or the output, and it's not the right equation, right? So I could say the equation is not right, or I could say it doesn't look like what I was expecting. But if you're a student and if you've learned the intercept rule in class and its derivation, I need to talk this. I say the output figure doesn't look right. I expected to use a different equation for the intercept rule. Your current version just uses the derivative of the G mix curve, but it should be something else. I'm too lazy to type it all out because it should figure out what it is, right? So it says, you're absolutely right. You need a common tangent to G mix that connects the free energies of pure components. So it fixes itself. It gives the correct approach. Let's see if it gives the right answer. Yeah, maybe that's correct. That's probably the same way of writing it in an alternative format. And then we'll just wait a moment for it to generate the text, and then we'll plot it. So it updates the code. So if I was a student and I didn't know that it was wrong, or if I looked at the figure and I was like, that's good enough, you would get 0 points on that problem, because it's not hard. Like, you don't get partial credit for like producing code anymore, right? MATLAB produces code. Our Chat GPT produces MATLAB code, and so now all of the assessment comes down to whether or not a student recognizes and understands what it's supposed to be doing.
But I would think, if I was a student,
Yeah,
and I saw you doing this in class,
yeah,
I'd be like, yeah, easy for you to say because you've spent your whole career doing this.
You're absolutely right.
Of course, you know what the right equations are. I'm
Right.
still trying to figure it out. So I would ask you, I would raise my hand
Yeah.
and say, Professor Sun,
Yeah.
could you give me some examples that I could benchmark
Sure.
against? And then once I could get the right answer for something I knew,
Right.
and then now ask me a question that's a little deeper,
Yeah.
and I'll see if I can use what I've learned to
So
approach it.
So the context of this lab is, again, after they've taken thermodynamics, right? So in
Right. principle,
they've already had lectures about these ideas. They understand. They've taken pencil and paper exams on these ideas already. And so the students, I wouldn't teach phase diagrams starting with this directly.
Okay.
Yeah. So I would teach regular lectures for a while,
Okay.
but then say, instead of our traditional homeworks with phase diagrams is like, look at this known phase diagram and use intercept rule or use like lever rule to like calculate phase fractions. I think that is probably not very interesting anymore. I think that, being able to plot a phase diagram, there's a lot of depth in here.
But all the homework you gave, all the things you did in class, those are examples.
Those are still things.
And so they should try to reproduce that first.
That's right.
And then see if they can extend it
Absolutely.
once they have the right equations and it's working.
Absolutely. And I'll show later like what kind of things you can do once you have a code that produces phase diagrams. You can start to make that matrix of omega.
Well, you did it at one temperature.
Yeah.
Now what happens at another
Exactly. Or I can change some of these parameters. I can change the interaction term, right? So by the way, so this is me. It's also worthwhile. I'm not doing it right now because I don't know how much time we have in the podcast, our viewers' attentions. But like, you can walk through the code line by line and discuss from a pseudocode level, like a logic level, what is it doing, right?
Right.
And I think that that's also very, very valuable.
Sure.
Let's try the code and see if it produces the result.
Again, I have a problem for you in thermodynamics.
Okay.
That is not easy at all.
Yeah.
And no one even knows the right answer.
Oh, well then, we'll talk about that in a moment. So once again, it produces the wrong answer. And so I'm just going to say, okay, then you can start to be rude with it. No, I'm just kidding. We want to choose a point on the G mix curve that has a given composition, say x equals 0.4, then construct the tangent plane at that point, then look at the intercepts at the y-intercepts at x equals 0 and x equals 1 to get the chemical potentials. You are not doing it correctly because you are not assessing the G mix at the composition. This is literally how I talk to my grad students too, right? Or not literally, but like this is kind of if a grad student gives me something and it's not exactly what I had in my mind, then I also explain to them that there is issues. And so this kind of skill set, I would say, is also quite important. So you're absolutely right. We need to blah blah blah. So in this prompt, I'm being a little bit more explicit about what I want as opposed to this one. This is kind of like limit testing, right? This is me asking something that is quite not being precise enough in what I want, and it's giving me a bad result. And now I'm being a little bit more precise, I hope, it's going to give me a good result. That gives me the value that I need. Let's take, so while this is running, okay, so let's copy. Let's put it into MATLAB and let's try again. Now I can manually edit it. Okay, so now it's getting stuck and it's not being able to find the result. So I'm gonna do one last thing before I move on. I'm gonna say I'm gonna give it the actual equation and then see if it can implement. You are still using the wrong equation for the intercept rule. It should be mu a equals g at x minus dg dx times x, and mu b equals g of x plus dg dx times 1 minus x. Now, I probably could have gone into MATLAB and implemented this myself.
Right.
Anyway, this problem is a good illustration of.
But it parsed it exactly.
Yeah, it parsed it right. Yeah, and so, by the way, this is the free version of Chat GPT, so it's not very smart. When you pay for the higher level versions, its memory is bigger, its knowledge base is larger, and so it does these things more effectively. I can show you what it looks like on my paid account, and I think it, I didn't have this many errors when I used it on my paid account. I'm not trying to shill for Chat GPT. I'm just telling you as an instructor certain resources.
The general thing is, we all talk about teaching students how to be critical thinkers.
That's right.
And this is being self-critical of your own work.
Yeah.
Is the way we always learn everything.
Absolutely.
That's what you do when you work with your graduate students.
Yes.
And that's what you're doing with Chat GPT. And look at that, it got it.
It got it right. It took a while, but it got the right result. And let's see if it outputs. Let's see if it outputs the. It didn't give me the numbers, but I can just right here. I can just delete the commented outlines. And by the way, now what you can do with this tool is you can start to play with the numbers. Just we were doing earlier, right? Omega. Let's do like 1,000, and let's see what the results would be. Sorry, start over. Maybe this needs to be 5,000 at this low temperature. There you go. So now you get new chemical potentials.
Yeah.
And so the value of this work is that a lot of these numbers, a lot of times when we're teaching in class, we're drawing on the board. We're being very qualitative.
Right. This gives you real values.
Exactly. Reducing to code allows us to produce real value. And there's a lot of value. Sorry. There's a lot of added value. There's a lot of, it's very valuable to have numbers, because when you have numbers, you have a sense of, okay, this is how T delta S competes with delta H at these temperatures, at these mixing enthalpies. And that helps you be more quantitative in your understanding, right? If you say like, oh, the moon and the earth are, the moon orbits the earth, and you're like, okay, that's one thing. But you say like, oh, but the moon is, 186,000 miles away or whatever. And then like now, and you say like, this mile is, this is in this many units away of Earth. And anyway, you have a more precise picture of the true structure of that relationship. And now when you get real numbers here, you can also be more, you're more able to compare numbers between different systems, between different chemistries more meaningfully. And that's very, very important. Okay, so let's get to the phase diagram, because that's kind of what we all want to see, right? So the phase diagram in this, we'll do the left picture first, right? This is the competition between two phases, a solid and a liquid at different temperatures. Now, I'm going to produce this first, and it's going to give you the wrong result, and then I'll show you why it gets the wrong result. But the important thing is that the solid and the liquid, their relative offsets also change with temperature. So at low temperature, the liquid is much higher in energy. At high temperature, the liquid is much lower in energy. If I don't say that, it won't know it. And this is something I learned in class when I was doing it live demo. But now I want to make a phase diagram with two competing solution phases. One phase is a liquid, and the other is a solid solution. So for now, let's have the omega values for both phases be, well, okay, let's have the omega values for solids. The omega value for the solid be positive, like let's say 5 kilojoules, And then for the liquid, let's make it an ideal solution. So I want to plot two solution curves for these two phases at a given temperature. Then, so, in class, what we would say is we would plot these two curves. You would take the convex hull. The convex hull is the lower convex envelope, and that would produce these two-phase coexistence lines.
Yep.
And then use that to plot the phase diagram. So then determine which phase is the equilibrium phase at a given temperature, which phase for coexistence of two phases is the equilibrium phase at a given temperature, and then use the convex hull algorithm to do this. Okay, so again, because I know precisely what to type, I can tell it to do this. And even if I tell it in this precision, it might get the wrong result. A student's skill now needs to be the capability to prompt the AI to do what you want it to do. Because if you tell it something that's a little bit off, it will give you a bad result. So the precision in which we provide instructions is now a new skill that we have to be very thoughtful about. And also, the precision in which you provide instructions to Chat GPT also reflects the precision to which you understand the information. And that's something that, like, if you're giving it bad results and it's giving you bad results, it might mean that your own understanding is incomplete or misleading. Great plan. We'll proceed step by step. So this is kind of the pseudocode algorithm for how you do this. And so let's try and see what happens. Let's see if it's done first. Oh, it's done. Okay. So I'm going to copy. I'm going to go to my code, edit PD. I'm just going to replace it all. Oh, sorry. I must have not copied it. Copy. Okay. And we'll run it again. Okay, so this is at a given temperature. And now so what's it doing? So there's a liquid phase, which is probably the blue curve down here. There's a solid curve. And it's taking the convex hull, which is like this bounding envelope between every single data point.
Right.
And so this is kind of the correct result, but there's two things that we think are wrong. The liquid free energy should not be the same as the solid free energy at a given temperature, right? They both change with H minus TS. And so I'm going to tell ChatGPT to implement that now. The free energy of the pure end members for both liquid and solids should be a function of temperature by G equals H minus TS. The liquid should start with higher enthalpies, but also has a higher entropy relative to the solid. Can you update the code to reflect this? I went to correct a typo, but ChatGPT doesn't mind typos. It knows what you're saying. Good idea. We'll update the free energies to look like this, okay? So now let's try. We'll see this.
How do you know when the code is finished? The little black dot goes away.
The little code box will end, and then it'll start saying explanation of the code. This feels a little bit like Bob Ross painting. As you paint, you're talking about all the things. Okay, so we'll copy this, and then we'll plot it and see if it looks better. So this is more of the right idea, which is that, so the liquid, remember the liquid is, you can't see the liquid because the convex hull is blocking it. I can do this. I can say, well, I can do this manually, but I can make the line width of the convex hull smaller and dashed. So like I know how to do this, but if you wanted to tell ChatGPT to do it, you could do it too. Okay, so now you see kind of what's happening.
Right.
Yeah. So let's try playing around with it a little bit, because this is where a lot of the interesting things happen. If I go to low temperature, let's say like 200 degrees. Now you see that the liquid is competing with the solid solution. So the solid solution is stable down here, and the liquid solution is stable over here. If I look at the phase diagram, indeed, you do get some of these curves showing up at low temperature, which is You get a little bit of solid solution here, and so it's coming down here. Then you get this tie line. Right now, the tie line is interfacing with the liquid, but again, these kind of depends on the numbers that you put in. You can play with the numbers until you get shapes that look more similar to this.
Right.
So now let's do a for loop in temperature, right? Because that's what a phase diagram is. I now want to construct a temperature composition phase diagram. Please run a for loop in the temperature range with the above code, and then plot the equilibrium phases with the same color that we were using for the tx coordinates where that phase was stable. Okay, and I don't know if this is gonna work on the first try, but let's give it a shot.
What do you mean TX?
Oh yeah, so Tx is like is a way we say temperature composition, because it's a temperature axis and an x-axis where the x is composition.
And it knows that.
And it knows that, right? And so like if you know,
So that's jargon.
that's my jargon, yeah.
Well, but it's not just yours. It's probably everyone.
It is,
and so because it's getting all of its training from looking at the web,
right,
it's getting the jargon as well.
So I'll say one thing about the training from the web, which is that a lot of computational code to execute computational material science is not on the web in a well-commented form. And so even if code exists, I think if you were to train AI, it doesn't necessarily know what it's doing. And so I feel like, AI is very good at producing like websites or like HTML or CSS or JavaScript or whatever, because there's a lot of code to teach people how to do these things and it's well commented. But for like in computational material science, we're all trying to solve we're trying to solve material science problems. And so the code is not very well commented. So I have found in my experience that that trying to do computational work with Chat GPT doesn't go very well, because I think the training is not very well done. And so that's why you might need to rely on this more. Okay, so now I've hit the free plan limit for GPT 4.0, and that's okay. I'll show it to you and let's see what happens. Okay, so that's totally wrong. Okay, now so I'm gonna switch over to my paid for plan just for the sake of this.
Sure.
Just for the sake of this demonstration. But yeah, it's true that you hit a limit, then you have to wait it a little bit later to continue using GPT. If you pay $20, I think you don't have a limit on 4.0. I'll just open up the previous assignment where I did this, and we can see kind of where it plays out.
Sure.
So here's phase diagram. I think it's phase diagram MATLAB model. Okay, so I'm gonna go back a little bit. Which model is it? Oh, this is O1 Pro. Okay, so this is okay. So I'll show you this in a minute. This is me using the thinking model and showing that it's not very good, or it's not very good. It's not very good. It's just it doesn't give you the right answer in one shot.
But you can iterate it and we'll learn from it.
Yeah, probably cut this bit where I'm trying to find the right code.
So you do this in class and show the students?
I do this live in class,
and then you give them an assignment and ask them.
Yeah, and so I'll show you. So this is okay. So let me show you this last bit. So I like to make the liquid solution be at a higher Gibbs free energy. This is kind of what I was just talking about earlier. And then there should be different offsets for both sides, A and B. Can you do that? And then I said, okay, please keep it. So I was playing with the code on my own end, but it wasn't updating here because I was playing with it on my own end. So I wanted to update its memory to have the code that works. And I said memory updated. Okay, now I want to write a for loop in the temperature. So it does this process multiple times. I then want to save the equilibrium state, which is the lower convex hull, and plot the stable phases and two-phase coexistence regions at each temperature. Then I want to plot everything on a binary TX phase diagram, temperature composition phase diagram.
Right.
So let's I'll just run through the previous. This is like Martha Stewart putting a chicken in the oven and then like bringing out a fully cooked chicken. So we'll try it. Okay, so now it's kind of doing the right idea. It's making multiple temperature slices. It's plotting those. Is it going to make the phase diagram? It's still running. It hasn't finished running yet. And now it makes a phase diagram. And is this right? So we'll think about it for a second. Now, this doesn't look like what I expect, right?
Right.
But like, let's see if it gets. So it is getting some things right. So it's getting this two-phase coexistence over here correctly. The liquid. Oh, this should be blue. Yeah. So if this were blue, that would be good. So let me go back to my code, and I probably wrote this last time. I made a mistake. The liquid offset should be a function of temperature too. Please write the liquid offset as a function of the enthalpy of melting and the entropy of liquid for pure A and B phase. Okay, so then I go back to my code, and then this is something I did last time, and I knew I looked at it last time and I figured out what was going wrong, and so I'm just gonna do PD. Okay, so still doing it wrong, and then I went back and I said, what did I say last time? Can you double check the code to see if it's properly taking only the lower convex hull at each temperature? Ah, that's what it's doing. So the convex hull bounds all the phases, but notice that the convex hull is also bounding the top side. And so that's incorrect. And so this is debugging, but instead of debugging, what is it? 74 lines of code. I'm now instead of debugging the code, I'm debugging with ideas, right? And now I'm saying to debug with and saying I need to map the convex hull. So it needs to produce all this. To get the lower envelope only, here's an outline of how to modify my code. And I think I probably just said, can you just update the code? Because it was trying to give me just the changes, but I said, just give me the whole code. So yeah. I do that. So this is still taking a bit of time, but it should. Again, this would have been a 2-week graduate thermodynamics lab. So, you know, we are flying through this assignment right now, even if it feels like it's taking a little bit of time and it's a little bit slow. This is extremely fast relative to what we expect. Oh, sorry. I cut it off during the for loop. Sorry, I need to stop it. Is there a way for me to call stop? Okay, I'll do it one more time, and I'm gonna make the its temperature range is okay, but I'm gonna make the grid spacing a little bit less. It's like 25, so it doesn't run for so long. Yeah, just speed it up a little bit for the call. Okay, doesn't look very good. The temperature range is probably too high, so I'm gonna make the temperature range from 100 to, let's do like 10 degree slices to like 500. And again, I know to do this because I had already played around with some of these numbers earlier, and I had a sense of what the what a right answer is. For students to get these things and not know how to diagnose it, these are again thermodynamic intuition rather than coding issues. And I think that what you want is for students to develop thermodynamic intuition. Right. Okay, this looks pretty good. If you look at this diagram, let's see, you get a lot of the essential features. You're getting the low temperature miscibility gap. Do you see this? Right. Yeah. You're getting this high temperature lens right here, the azeotrope, and you're getting the solid solution region. Now, what it's not doing well is it's not coloring these the right way. This should be blue, and this should be probably red, and this part is fine. So let me just go back to Chat GPT and tell them to update the colors correctly. I'm sure I did that. Let's assign colors for each phase. Let's assign red to solid solution and blue to liquid solution. Plot it, and then it's going to do all this. I'm going to copy. Okay, so now, look at how complicated this code is. It has a helper function to identify what is the lowest energy phase and which phase that belongs to. So it's a lot of work to do manually, but for ChatGPT, I just said match the phase to the proper thing. Let's run the phase diagram. It's gonna. I made an earlier change to the temperature and the density of the grid, which you probably didn't remember, or I didn't know to do that. So I'm just gonna manually do that again. So temperature range from 100 to 500, and we'll do like a 10 degree interval, and we'll just do 25 grid points per on the x-axis. Let's try again. Okay, so you know this legend is really painful to look at, but let's see how the phase diagram looks. Oh, you know, I should probably clear my old one. This is the right one.
Oh yeah, look at that.
So it's pretty good.
I don't
It's
know what's
pretty
going on the right.
Yeah.
One.
So anyway, issues are happening. It's not perfect, but hey, this diagram, for me, coding with all my expertise, with all my MATLAB skills, with all my Python skills, all these things, this would take me a good afternoon to code and pull off properly. Like, you know, 5 hours probably.
Yeah.
Without Chat GPT. But you just saw us doing it live in
5 minutes.
5 minutes. And I'll show you one last thing, which is the more complicated version, which is a eutectic phase diagram, is a lens phase diagram. In a eutectic phase diagram, you have 3 competing phases, alpha, beta, and liquid. And I'm probably just going to go to Chat GPT and find the final result. You can see can see on my scroll bar that I did a lot of back and forth.
Right.
But I stopped on this one, so maybe this is the right one. I'm just going to plot it. And then, so now you see there's 3 phases. Again, I'm going to go at a low temperature range. I'll do 100 to 500, and I'll do the spacing 25. Let's see how it does. So okay, it's pretty good.
It's not bad.
Yes, it's pretty good. I'm just gonna change the numbers again to be a little bit more. So I'm gonna do 10 degrees, and I'll do like let's do like 30 grid points. And you can, of course, once the code runs, you can make it a denser grid, as you wish. It'll show up in a second. Oops. So here's the G curves. Here's the phase diagram. Here's the G curves. Look at that.
That's amazing.
This is a eutectic phase diagram. And now that I can do this so quickly, well, first of all, let's appreciate this for a second, right? It is remarkable that in the however many minutes that we spent, that we can get to a eutectic phase diagram in MATLAB in less than, I want to say, 30 minutes, an hour, right? And earlier I ran into the GPT-4 limit on the free account. If you pay $20 a month, you can keep on iterating. But you can see that you can go very, very quickly. This is the kind of stuff that, like, normally, like, what we didn't do in this little demonstration is we didn't read the code. But now that the code is here, students can go and read it and study it and think about what's happening. And if they don't understand a certain section, what is a temperature offset? Like, what is this doing? So let's just try. Yeah.
Chat GPT.
Yeah. What is happening in this code section? And just for teaching's sake, I'm going to change the model to 4.0, which is the free version. Now think for a second. This section depends. So now you can ask here what's happening, and it will do it for you. It will.
So you don't need commenting anymore. You just ask it for the comments when you need it.
You can ask for the comments, but you can also ask it to teach you when you need it. Like, you know, you can have it explain conceptually why it's doing. Why is this needed? The liquid phase free energy should be higher than the solid phase at low temperatures. At high temperatures, the entropy contribution pulls the Gibbs free energy of the liquid down.
That's awesome.
This is fabulous, right? And like, if students don't get it, you know, you can go through, you can read through it and just read every line and understand what's happening. And so this is also super valuable. You know, let's talk about this. Helper, determine which phase is stable. This stuff is like pretty complicated stuff. So like, what is happening in this bit here? What is the logic of the code? Can you provide it to me in pseudocode explanation? And so it can tell you what it is, and it can tell you how it's matching one phase to another phase. Again, me writing this and figuring out the logic and executing it would take some time. It would take like an hour probably to figure out how to do this. So students can learn this, and like we said earlier, the main advantage was I was teaching not this, but I was teaching this thing where we were changing the numbers and seeing different kinds of phase diagrams, right?
Right.
So let's try this. I mean, just for a moment, let's try to make this phase diagram here, okay? The liquid is a plus 20 kilojoules, and the solid is plus 15. So let's see if it'll make this offset. So solid solution will plus 15, and then the salt we'll just do 10, and then for the liquid we'll do, well, it doesn't seem like it has one. Oh, so it doesn't have a liquid mixing enthalpy. Well, let's just try one
Because
thing.
you said it was an
Yeah.
ideal
Yeah,
solution.
that's true. So let's try one thing. I'll make one of the phases have a high mixing enthalpy and one of the phases have zero mixing enthalpy. So if I was a thermodynamicist, we would say, what do we expect to happen to these solid solution regions? The section with no mixing enthalpy, no positive mixing enthalpy, should have a wider solid solution regime
Right.
than the other one, which has a very positive solid solution mixing energy. Let's see if that comes out. So clear all. And then actually I'm gonna make it so it doesn't plot this other one because it seems to be really messing up the figure.
So how do the students respond after trying this?
Great, I'll tell you in a moment after we.
I guess the better question is.
So it made something. I made a mistake, which is I put it really to 0. This phase diagram looks more like the lens phase diagrams that we're looking here. So you're getting a full solid solution regime.
Right.
You're getting this whole thing, which was perhaps my mistake. Give me 1 second. I'm going to try to fix it. And then earlier, these numbers were 5,000 and 5,000. I'm just going to make it 5,000 and 2,000. And I just want to see. It do it. And I'll respond to your question while it closes. Again, this is me kind of teaching. This is not a podcast. This is not a demonstration for the students. This is a demonstration for the teachers. So I'm assuming maybe that you already know how to do a little bit of this or think about these things. And so I'm going very quickly. When I work with students, I go a lot slower. So yeah, look at this. The solid solution regime is much wider for one than the other when I played with the numbers. Now that makes intuitive sense to me, right? But it also should be like it's a great now you can say, oh, when I have it to be 2,000, now you can get 40% solid solution versus what is this? 10%, 6% solid solution, and you can get real numbers. And I could of course make this grid denser so you can run the calculation more so. So this is the advantage of computation, right? You can really play with numbers and see what the effect of that on.
And I suppose you can ask, one of the most common questions I hear with the iron carbon phase diagram is, why does iron go from BCC to FCC?
Sure.
And while
back
that's
to
a
BCC.
deeper, why it's a deeper question than even the thermo is going to answer. You can at least understand how the thermodynamic variables would actually predict it.
That's right.
The deeper answer has to do with electronic
magnetism. So the iron carbon phase diagram has a lot of interesting things going on, but I'm pretty confident that if we wanted to, we could reproduce the iron carbon phase diagram in using the same kind of methods that we're doing. There's 3 competing polymorphs on the iron side. There is an iron carbon phase that's really far out. It's at 25%, right?
Yep.
But really, the paratectics, the eutectics, this large solid solution region for the FCC.
So this tool allows you to then think about all of these things, and it allows you to go to additional dimensions by adding in the kitchen sink of different elements to get what you want.
Maybe this should be the homework assignment.
Yeah.
Like I was saying earlier, what I just did could be the in-class demonstration.
Right.
Now tell students, okay, that was fun for us, right? We did that in an hour. That was like 1 lecture's worth of stuff. For your homework or for a class project, maybe like a bigger than a homework. But now use the same tools to produce energies that would give you the equivalent result of the iron carbon phase diagram. And this is, like I said, there's a lot of
but the power I see in this is these are new tools for alloy designers, and they don't even have to learn how to code.
Absolutely. I don't want to say anything negative about existing software, but thermodynamic software is very expensive.
Yeah.
All right. I'll just say it. Thermocalc is very expensive. Thermocalc is extremely expensive. And Thermocalc does a couple things. It has a phase diagram calculator, but it also has a database. The database is really where all the value is, in my opinion. The phase diagram calculators I just showed you, you can calculate phase diagrams in MATLAB write the code to produce it very, very quickly.
Right.
And if I were to spend a couple more days working at this speed, I could have whole software suites. I could have very powerful things. In fact, I will show you one very
You
fast.
can build your own database.
And we have it in my group. But
Yes. But you get to go beyond the databases that are even in very full programs like Thermocalc.
absolutely. Let me show you something that this is me. This is something that a student did in my grad thermal classes extra credit. But this is what we were doing earlier,
Right.
and he implemented a slider on here, and so I can now do sliders with the
Oh, cool.
with the terms, and you can see how the phase diagrams change shape. You can put the liquid mixing entropy. Here's me playing the liquid mixing.
But you can go to ternaries and quaternaries
totally
and do
could.
different slices
You
and
totally
all
could.
of that stuff.
And I want to show you what else is cool about here. You can also see the Gibbs free
Oh,
energy
there you
surfaces.
go. Yeah.
So we're taking the lower convex hull, but you can see the actual free energy surfaces. Again, just as a little
That is
plug.
so cool.
The way to get here is my research group is whsunresearch.group. You go to visualizations, you scroll down to regular solution model. And so this is like, you can play with all the terms that are needed. I can play with the enthalpy offset. I can play with every free parameter in this model, and you can see all the phase diagrams that can emerge from it. And like, I did the thing in MATLAB earlier, but you could, with a couple more days of work, you could produce something like this.
So let me ask you
Yeah.
a question I've been dying to ask you
Yeah, please.
the whole time. It has nothing to do with education,
Yeah.
but everything to do with my research.
Okay.
So with ultrafast laser interaction with materials, we
Yeah.
can bring materials to extreme conditions.
Sure.
None of this crap like you hear about extreme materials.
Yeah,
like
super
TMS.
extreme, like sun extreme,
I'm
right?
talking
Yeah.
about
yeah.
getting to the critical point of tungsten,
Yeah, sure,
right?
sure.
Which is,
Like,
you know,
you mean you mean the place where the solid liquid vapor is super critical point?
exactly.
Yeah.
And but I don't see any difference in asking questions about that than
No.
what you just showed me.
I mean, there's no.
But there's no data,
Exactly.
right? There's no database.
Right.
No one's even tried to do it before because most people don't care,
Right.
except weapons designers.
Sure.
But it's really important for ultrafast laser solid interaction because we can get to the critical point.
Sure.
And I've been working with Ben Tarava, who's
Yeah.
been doing this from a stat mech perspective, looking at density temperature
Sure.
phase diagrams.
Sure.
You get this thing called the vapor dome,
Of course.
which is a
A classical derivation.
spinodal-like
Yeah.
region where liquid droplets and gas bubbles
Of course.
coexist.
Right.
At the very top of that is the critical point
Right,
where
right,
you
right.
get explosive boiling.
Sure.
But that's a really hard thing to think about. Yeah, we access it every day with an ultrafast laser.
Yeah. So it's not. So if you mind, this is my perspective, and not to say anything about StatMech, but you can fit what the enthalpy of mixing of the solid liquid coexistence phases with, or not solid liquid, but liquid vapor. You
Yeah.
can fit what the interaction energies are there by writing the code to make a liquid vapor dome, a liquid vapor coexistence dome, right? You could write the code to do that, and then if you experimentally know that the transition temperature is 5,000 Kelvin or 7,000 Kelvin, then you can play with the numbers until you get 7,000 Kelvin on your calculated phase diagram.
Right.
And now you can see what was the number that gave me that result. Now you know what that number is. And that number is probably related to the cohesive energy of tungsten. It's probably related to the cohesive energy of the liquid phase. And you can do it from the van der Waals gas derivation from StatMech. You can do all the math, and you can go back to the interaction energies in there too. My point is that what is complicated is the idea. What you just explained to me, the idea, right?
Right.
The idea is not that complicated,
Right.
but the implementation is a lot of
writing
work.
the code to
Right.
actually do that is really
And so if you know what the idea is with very high clarity and precision, tools like Chat GPT can help you execute your intention very quickly. A lot of times I've had ideas in my mind that I wanted to reduce to practice. And like, if I had to sit down with a pencil and paper and work for 4 hours, then I feel like, I'm just a little bit too busy to do that right now.
right.
But with ChatGPT, I can spend like 1 hour and get further with pencil and paper than I could doing all of that stuff.
Yeah.
I'll give you just one example. I was writing a thermo exam problem last year when there was Hurricane Irma around, and so I heard that hurricanes are Carnot engines. You can model a hurricane's power from the surface temperature of ocean with the atmospheric temperature up there, and then use that as a Carnot engine to see how much work it's producing, and then use that to get the maximum hurricane wind speed. What a cool idea, right?
Yeah,
For me to execute that would have been a lot of work.
sure.
Me working with Chat GPT, like 1 hour, I had a beautiful exam
Awesome.
problem that could be solved.
Well,
Yeah.
you've convinced me.
Yeah. Okay.
You've convinced me that this is the right way to teach students how to use Chat GPT
Yeah.
so that they have a powerful tool to do whatever they want going forward. This is
Absolutely.
incredible.
I just want to conclude with just that first slide that I showed again. Right. ChatGPT helps us execute a lot of the basic things, like the regular solution model, the convex hull, the plotting of all those things. It helps us execute a lot of those things really quickly. And then we as humans, I would say producing the phase diagrams kind of at this green level, analyze and apply kind of stuff. But like for you to say, why does the argon carbon phase diagram have that shape? That's a really high level question. And students can try and assess that now. Or if you can say, why does the vapor dome of tungsten have the number that it has? Or what is the number of the mixing enthalpies or the vapor energies or the bonding energies? You can now assess that kind of question. And that kind of question that you just gave me about tungsten, that came from your research, the kind of questions that you've been working on with lasers and that, like, that's the kind of stuff
Right.
so ChatGPT would never answer that by itself. Even if we have artificial super intelligence, which is what people are trying to build, right? Things that are smarter than humans. They still don't necessarily have the questions to ask that, in all of us, we have our own questions, right? And so right now we have to become really good at asking questions.
Yes.
Interesting questions that are at a high level, that are grounded in our experience and the kind of problems that we are trying to solve in the communities that we're trying to solve. And then ChatGPT can help us. Again, we have the intent, we provide the intent, and ChatGPT and all these other tools can help us execute on these things with a lower barrier.
Fantastic. I think we're way over time. but
Okay. Yeah, this is a lot of fun. Thank you so much for having me. Yeah.
Yeah,
Thanks a
happy
lot.
to have you. And to everyone
See you
out there,
later.
we'll see you next time on the next episode of Undercooled.